Thanks again. So the lecture today is on a bit of a different topic, although as we'll see at the end, it is somewhat related. It's about another phenomenon that's been observed in deep networks, and it's this phenomenon of adversarial examples, a kind of brittleness property. So this is joint work with Seb Bubek and Yeshwanth Cherupanamjeri. Seb is at Microsoft Research, and Yeshwanth is a PhD student in computer science at Berkeley. So the practitioners have observed that some of these deep networks that are so effective at prediction problems have a very strong sensitivity to changes in their inputs. So this is an example. So they've found that if you take a network, for instance, trained to predict labels of images. This is an Imagenet example. So 200 class classification problem, looking at different kinds of images, and you can take an image that this network so this trained network predicts accurately. In this case, it's a panda, and slightly perturb that image and produce a very different classification. Okay, so the confidence is here. These networks produce, in this case, a vector of dimension 200, and you can think of that as being like a nonlinear logistic regression model. So it's passed through a softmax. So they say confidence as a conditional distribution model, it's pretty terrible, but the point here is that you're going from something that, for this set of 200 classes, it's a solid prediction of a panda, the correct classification, and you can switch it to a solid prediction of some other label, in this case a gibbon. And how does that happen? These two images look essentially identical, certainly to me, but the modification here is very, very low in magnitude, and you find that modification that flips the label at the output of the network just by descending a gradient, with respect to the input. Right? So you want to find the direction in input space that maximally changes this output label. Okay, so this is not a very desirable property of these networks. It's actually quite a robust property. You see it, practitioners have demonstrated this in a lot of different circumstances. And in fact, not just, so there's a particular image here and you're computing the gradient with respect to that image to find the direction in which you can change things. Turns out that you can find a common direction that works for a large set of images. Which is, an equally striking property. Okay, we mightn't care so much if you're misclassifying pandas as gibbons, but of course these, or very similar deep networks are used for more safety critical applications. So for instance, in autonomous vehicles, in picking the difference between, a stop sign and a speed limit sign, this is something you'd be more concerned about getting wrong. It turns out, and this is work by my colleague at Berkeley, Dawn Song, and her group, turns out you can identify some small modifications to make, again, a trained network that's very effective at this task of identifying traffic signs. You can find small modifications in a similar way, but in this case, the idea is they wanted to find modifications of an image that involve just, physical perturbations, right? So sticking stickers on the stop sign, and you could get that sign misclassified as a speed limit sign. And the point of the photograph of the graffiti on the stop sign on a Berkeley street here is it's not so different from the sorts of things you might see on a regular stop sign. Okay, so there's been a lot of interest in this sort of phenomenon, a lot of work on trying to avoid this kind of sensitivity, looking at alternative optimization methods that work with a more robust notion of loss to try to avoid the brittleness property. I want to say a little bit about, in this talk, about why this property might be there. And we're looking explicitly at a very specific arrangement for which we can prove something. So it's not, I should say from the beginning, it's not a situation where we're looking at trained networks, the actual parameters that have been chosen based on a data set, in which the practitioners have identified this phenomenon. So we're thinking about a case that is easy to analyze, where the parameters are chosen randomly. So you could think of that as the initialization that these stochastic gradient methods use. And here's a kind of one-slide summary of the key result here. It's a specific kind of network that we're considering, specific nonlinearity. It's mapping from x to the notation I'll use is f theta of x. So the theta here is the parameters of this deep network with this particular ReLU nonlinearity. X is in Rd, and we're thinking of that dimension as large, like the image case. And the result is that for any input in this input space, and I say most parameter values, I'll get specific in a moment. We'll have an actual theorem. I'll stop waving my hands. But for most parameter values means, under a particular distribution, a Gaussian distribution with high probability, there is a step size eta, so that just by taking a step in the gradient direction, or the span of the gradient direction, you can modify that image and get flip the sign of the output. So I'm thinking here of a real valued function. So f theta is just maps to just the reals, and think of that as two-class classification, and we're just wanting to produce the opposite label. And the point of that perturbation term is that its scale is really small compared to the scale of the input x, right? So the ratios the ratio of the change to the input, to the norm of the original x, is like 1 over square root d, right? So in a high input dimension, this is a really small change in the input that leads to a change of the sign. Okay, and one other thing that I think is really interesting here is why this happens. It's because the function f theta, you can show it's very close over quite a large subset of the input space, very close to a linear function. And this is a kind of high-dimensional phenomenon for linear functions, as we'll see. Okay, so that's the kind of punchline. I'll be a bit more specific about the results, look at a little bit of at least more closely related prior work. There's been a huge effort by the practitioners to understand this phenomenon. So I'm really only looking at kind of the related theoretical work, and then present the idea of the proof of the result that I mentioned, and it really is based on this notion that we're in a close to linear situation. The result that I'll show you only really works for bounded depth, and it degrades as the depth of the network increases, and we'll see that that's actually necessary without, in the circumstances that we study. Okay, and then I'll tell you about some open questions and also a connection to the benign overfitting work that I talked about yesterday. All right, so that's the agenda. So let's start by being a bit specific about the family of functions we're considering here. You'll see I've marked it in red. I've dropped the subscript theta. The parameters are always going to be randomly chosen in a specific way that I'll tell you about. And these are the parameters, the W1 through WL+1, so there are L hidden layers, I guess. And the notation we'll use, the input dimension is D. The width of the network at layer I is D sub I. right? So W1 is a matrix of first layer parameters that you know, a linear mapping that takes you from RD to RD1. After that linear mapping, we apply some nonlinearity, this sigma function, and then another linear mapping defined by the next set of parameters hidden there, W2, and so on, right through to WL, and then we have a row vector WL plus 1. So I'm writing this nonlinearity as a function that maps from a vector, let's say D1 to D1, RD1 to RD1, and it's typically, you know, a scalar function that's applied component-wise. Okay, and the example we're going to be working with here is this, what they call the ReLU nonlinearity for rectified linear units. So it's just this piecewise linear function that's 0 to the left of 0 and the identity to the right. Okay, so this is the parameterized family of functions, and the parameters W, we're going to consider choosing those with independent Gaussian entries. And the scale actually doesn't matter. So if we look at the ReLU function, you can see that you can shift scaling from the input to the output of that function, positive scaling, I should say. All right, so if we scale up an input x, we could equivalently scale the output of that nonlinearity. So any scaling that we see through this network of these symmetrically chosen Gaussians, you know, we could apply it at any point in the network, so just by convention, so that we can easily keep in mind what the scale of various signals, scales of various signals will be. We're going to choose the entries of matrix Wi, which maps from, you know, the ith layer to the I plus 1th layer, or at least it's the linear part of that mapping. It's going to have variance, I said that wrong, from the I minus 1th layer to the ith layer, right? It's going to have variance 1 over di minus 1, all right, so that the scales of all of our real valued signals throughout the network are kind of on the same order, okay? Okay, you know, that's, and brittleness here is a convention. It's really not so crucial, but it makes our life a little easier in keeping track of what's going on. Okay, some other notation I'm going to use is this d min is the minimum of all of these dimensions. There's an input dimension d. There's the various widths throughout the network, d1 through dl. And then there's this scalar output. The minimum of all of those widths and the input is d min. And you know, correspondingly, Dmax is the max of those. L here is the depth or number of layers, layers of these nonlinearities. I'm going to write, they're called constants here, but they actually depend on L and they depend on a confidence parameter delta, right? So there's some probability of failure here, and you know, we'll have these constants depending logarithmically on 1 over delta, and also polylogarithmically on the various widths, the d's. So you know, I'm calling them constants. The assumption we have about the widths is that they're not too radically different from each other. So you know, widths that are polynomial in each other, bounded by polynomials in each other are fine, but there is a constraint on these relative widths. Okay, then the result is that for any fixed x in Rd with high probability, you can take the gradient of this random function, and by picking the direction and the step size appropriately, you can flip the sign of the output of that function. Okay, and crucially, the size of that perturbation, eta times grad f of x, its Euclidean norm is no more than something like 1 over square root d times the Euclidean norm of the original x. Okay, so we've got this huge sensitivity to a perturbation in that direction. Okay, so there's been, as I say, a bunch of interest. I'm really just focusing on the most closely related work. So there's this work of Eli Shamir and collaborators looking at proposing an explanation for the presence of this property. And they argued that in a multi-class classification problem, we should expect to find perturbations that are small in Hamming distance, in the sense of the number of components of the input that need to be changed in order to get a flip of the classification of the output should be small. Of course, Hamming distance isn't such an interesting notion of the scale of a perturbation, and it's easier to see that in the sort of cases that they were considering, you can have a very large change. Think of it as changing pixels in an image. You can require a very large change in a single pixel. Doesn't seem like the same phenomenon, certainly. So this work of Danieli and Shacham was considering Euclidean distance and showed a result in terms of these measuring scales of perturbations in Euclidean distance. The strange thing about this is they required this pretty stringent condition that the widths of the network were rapidly decreasing. Every width was very small compared to the width of the layer before it. And this more recent work was able to get around that constraint in the case of two-layer networks. And you can view the theorem that I mentioned as a kind of common generalization of these two results. And at a high level, the intuition is really the same. So let me say a little bit about that intuition. So, very, very easy example. Think about a linear family of linear functions, and we're choosing the parameter vector for that function in a symmetric way, let's say with a Gaussian distribution. So if you think of a fixed input vector x, and our parameter theta is a standard normal d vector, then the scale of the gradient, of course that's just the vector theta, is very tightly concentrated around root d, the dimension of the x. The scale of the function itself, of course it has a norm of x squared distribution, and so it's going to be, typical scale of f of x is the norm of x. Okay. But of course, the inner product and the product of those two norms are really rather different, right? This is just in high dimensions. We totally expect that. So when we take the product of the norm of the gradient of f and the norm of x, we see something that's much bigger than the typical scale of values of f. Okay, so if we were to change x in the direction of the gradient or the negative direction, depending on the sign of f, then we can flip the sign of f. And in particular, if we take the scale of that perturbation of x to be, essentially the magnitude of f at x divided by the norm of the gradient, we get a change of sign. And if you look at the typical scales of these things, that perturbation is going to look something like the norm of x, certainly no bigger than order of the norm of x divided by square root d. So that's way smaller than the norm of x. Okay, so in the linear case, this is a pretty simple phenomenon. We're just in high dimensions, and this is totally what we should expect. So the crucial thing is that the same thing occurs when our function is nearly linear, right? And we'll look at a smoothness condition that's going to quantify that. Okay, so essentially we're showing a near linearity property for these deep networks. So as I say, we're treating this depth as a constant and thinking about these C of L functions as values that depend on L. They actually depend exponentially on L for the result that we have, you know, for L a constant that's polylogarithmic in the widths. Okay, and as I say, we're going to fix the scaling. I told you about the 1 over di minus 1 to keep things constant. Let's think of the norm of x as being root d. So all of our kind of scalar signals throughout are like a constant. Okay, so everything looks like that. So all right, so why is this sort of random function approximately linear? So we've got our fixed x. There are kind of three parts to showing this neolinearity property. One is that the scale of the output of our network is not too large. The second is that the scale of the gradient is not too small. And then we have this kind of smoothness property, right? So in a neighborhood of x, we want to show that for anything that's close to x, and close here means sort of order of square root d min, you know, up to what I'm calling constants for constant depth. The change of gradient is small compared to the original gradient, right? Again, bounded by what I'm classifying as constants. Okay, the interesting thing here is over a much bigger area, but much bigger radius than we need, we have this neolinearity property. So it's sort of order of the square root of the minimum width, whereas all we really need is something like a constant in order to apply the neolinearity property to argue about this presence of these adversarial examples. Okay, and why is that smoothness property all we need? So, you know, if you think about our function in a neighborhood of x as we perturb things by some vector u and compare that to the first order Taylor series approximation, you know, you can integrate the derivative of f in the u direction, right? And you can see that the deviations between these two is going to be no more than how far you travel versus how much that gradient changes, right? And if we look at just the maximum of that in this ball of radius norm of u, you know, that'll give us a suitable upper bound on how well we can approximate this function by its by this affine version. Okay, so you know I've called it a smoothness property. Of course, it's not really smoothness, and I'm writing gradients here. You know, that's in a weak sense. These things aren't smooth, of course, because the gradient is not even continuous, right? We have you know, the ReLU there, but what matters is what changes over the scale of the move from x to a nearby point y. Okay, so it's a sort of medium scale smoothness property that we need. All right, so there are three steps here. You know, controlling scales of things and then getting this smoothness property. The smoothness is the most interesting, but let me say a little bit. You know, keeping these things appropriately scaled is not so hard to see. So just to point out a few of the tools that we use. So this ReLU function has the nice property that we can view it as an indicator times the identity function. And when we do that, we can rewrite the function computed by the network in this sort of linear form or linearized form. You know, we're replacing these indicators for the sign of the different components being positive by a diagonal matrix. Of course, that matrix depends on the input. And I'm writing it as h1 of x for what we see at that first layer of the network. the diagonal of these indicators. Okay, so when we write things in this way, then it's easy to see what goes on. You take your input x, you're scaling it by this Gaussian. We're losing some of the signal because of the diagonal matrix of ones and zeros. But okay, so the expectations are scaling in a way that leaves us with something that is a constant. I mean, we're losing perhaps a constant factor, or gaining perhaps a constant factor. In those nonlinearities, we don't lose much more than kind of half of the signal. And of course, everything's nicely concentrated. We have these kind of high-dimensional Gaussians everywhere. So if we look at in a particular direction, we get something that has a variance that means that where the norm of such a thing is roughly just the scale of that v. So it's unit norm for a particular direction. Okay, one other property that's really very useful here is the symmetry property of the ReLUs. So these HIs are the diagonal matrices of ones and zeros. We write our function in this sort of locally linear way, where that H1 is the diagonal matrix. I mean, I'm skimping on notation here. The diagonal matrix of these indicators of the different components being positive. We can exploit the symmetry of the Gaussian distribution by taking another diagonal matrix of plus or minus ones, and for any such, let's say S1, of course we have the same distribution of S1 times W1, just because of the symmetry of the W1. And similarly, we have the same distribution of W2 times S1, right? And of course, these diagonal matrices, S1 times a, indicator times S1, that's just S1 squared. That's always going to be equal to this thing. And so now we've got this, the S1's disappeared everywhere except in these indicators. So, that's, if we choose these S's uniformly on plus minus 1, then, we're actually just randomly zeroing out signals as we move through this network. Okay, so, this is very, very convenient for the analysis. Okay, so, this is true for a fixed X. Of course, we have to be careful if we're thinking about what happens in a ball around X, and we have to take account of dependencies there. Okay, and for the more interesting property, the smoothness property, we're doing exactly that. We're saying we've got this X and we want to look at what happens as we move around to a Y. How does the gradient change as we do that? So it turns out you can decompose. It's an easy induction to show you can decompose that change of gradient at the point X versus some point Y near X into what happens, a sum across layers of this network of, a product like this. You start out with the computation that you would do, the local linear computation that you would do around Y, followed by, a difference of the nonlinearities, these diagonal matrices, difference between X and Y at that layer J, followed by the computation that you do beyond that point for the input X. Right, so this sort of decomposition shows that if you want to compute how these gradients change, you need to keep control of, the scales of these pieces on either side, the scale of the mapping for Y, up to the jth layer, the scale of the mapping from the jth layer to the output for X, and of course keep control of the differences between these nonlinear functions at the jth layer. Okay, so just to say a little about keeping control of the scale as you move through this network, you can show that so let's introduce this notation. Fi is the function computed from the input to the ith layer, so it's this vector valued function. And the image of a ball in the input space, so around the point x, we've got a ball of y's, and you know, what we can show is that that image stays inside a suitably scaled ball at the ith layer. So you know, we're not too close to 0 at x, and for everything in a neighborhood of x, you know, we have this sort of Lipschitz property that if y is close to x, then the image at the ith layer is like square root di over d min times that. So you know, this is a kind of straightforward argument. You know, you need to use make things uniform across y. So use a sort of epsilon net to give something of this flavor. The problem is it's not good enough to get the sort of result that we want, because this di over d min is potentially you know, terrible. These things are sort of only within polynomial factors of each other. So we need to be a little more careful in keeping control of scales. And there's this notion of a bottleneck layer. So here, you know, just to give you the idea, I've shown, you know, a bunch of widths, right? We have an input of dimension d, and then various layers of different widths di. You know, and the notion of a bottleneck for layers 9 and 10, you know, 9 is the bottleneck. It's the narrowest layer from there on. You know, leading up to those two layers, and similarly 5 is the bottleneck layer for the next 3 layers, and then the input is the bottleneck for the previous ones. If we do things in terms of these bottleneck layers, then we can get the right control of scaling between layers. So rather than considering the input in the ball in the input space, we consider the image of that ball at the appropriate bottleneck layer and get a ratio that means we're keeping kind of tight control of scales of things throughout the network. It's this square root of di over dB here is the smallest dimension from the input up to that point. Okay, so the result has this form, you know, that we can perturb things in the direction of the gradient, and we get you know, the scale of that perturbation is like 1 over square root of d times the scale of the input x. We actually had the neolinearity property you know, over a much bigger range than just this constant. It was up to sort of square root d min. So you know, very significant ball in input space where these networks are computing something that's really rather close to a linear function. One thing that's not so nice about the theorem that we have is that, you know, we're treating this depth as a constant, but things actually degrade pretty badly as a function of the depth, right? We're getting you know, these C of L's that appear everywhere exponential in the depth L. So you know, things are certainly getting weaker as that depth increases. Turns out that's inevitable. So you can prove a converse result, inevitable at least under the circumstances that we've studied here. So you can prove a converse result. Let's keep the widths all constant at k. Consider a depth that's polynomial in the input dimension d. As long as that width is polynomial, at least polynomial in d and k, and you know, don't believe any of the exponents here, and certainly smaller than you know, not too large in terms of L. Then with significant probability for every pair of inputs in the input space of the same norm, right? The ratio of the change of output to the output for one of those points is like 1 over square root d, no more than 1 over square root d. So you know, as this depth increases, you have something that gets closer and closer to computing a random number times the norm of the input. right? So, you know, you have an essentially, at least on the unit sphere, say, you have an essentially constant function. Right, so this is really very far from the situation where we're seeing adversarial examples. Let me say a little bit about why that happens. You know, there's a sort of, this is a step in an inductive argument. If we imagine we've got two inputs, x and y, and up to layer I, we've got the representation at that layer, fi of x and fi of y, and perhaps those two have some angle between them. I've written that here as theta I. Then, you know, what's the angle? How does the angle evolve as we move to the next layer? You know, you can look at just the expectation. So, you know, it's a correlation between those two. The Z transpose here is this appropriate vector of Gaussians. So, you know, this is just a computation of a double integral to see how these things are scaling, and we get, you know, this expression on the right, the sine of the angle over pi plus 1 minus that theta I over pi times cos of theta I, and if you look at how that plots, so this is showing theta I over pi versus cos to the minus 1 of that quantity up above. So this is theta I plus 1 over pi. You know, you're getting something that's rapidly converging to 0. You know, and you can get an idea of the rate of convergence. So this expected angle is decreasing like 1 over L, and if you're a little more careful and prove things in high probability, you get the kind of result that I described. Okay, so you know, there's this quite a gap in the dependence on depth, right? So for the result that I showed had something that, you know, if we ignore the log 1 over delta kind of terms, we see something like an L to the minus L times this root d of the ratio of scales. On the other hand, you know, when we're in this deeper situation, we see, first of all, this function is very close to computing just a ratio of computing just the norm of the input. And so, you know, if you look at the corresponding ratio of the corresponding smoothness property, you know, we don't see anything like the situation we saw before, and certainly, you know, having essentially constant output, we're not seeing this adversarial example phenomena. Okay, so, you know, big gap between this exponentially small lower bound in the case of fixed depth, the first theorem I showed, and this polynomial dependence on depth in the converse result. So this is, you know, I think an obvious question. I think a more interesting question, you know, more pertinent question is what happens when we move away from this random choice for the parameters to parameters that are actually chosen through an optimization method like a stochastic gradient kind of approach that people actually use in practice. And you know, in particular, do we keep some of this approximately linear behavior that we see in randomly initialized networks? So I think that's a really interesting direction. I'll say a little more about that in a moment. But I wanted to point to a connection to the lecture from Tuesday, this phenomenon of benign overfitting in the last few minutes. So so if we think now about, you know, this linear regression example that we looked at on Tuesday, and, you know, think about the random choice that we saw that I described here. You know, this simple phenomenon that with linear functions we see this kind of sensitivity. You know, they do suggest two rather different potential causes for adversarial examples. So just to remind you of the setup from Tuesday, we're talking about linear regression problems, right? So input vectors x, real valued responses under some assumptions on this joint distribution. We have the covariance of the x's, the optimal linear prediction rule, the parameters of the optimal linear prediction rule, the expected squared error of that thing, and we take our sample of size n and compute the minimum norm linear prediction rule that gets things perfectly correct on the data. So we're assuming we're in a high enough dimension that we can do that. So the dimension here is small compared to the sample size, and we're interested in this excess prediction error, the expected squared error for this estimator theta hat versus the true theta star. Then we saw this theorem on Tuesday that the excess risk is bounded above by hiding a bias term. Two terms. And we better have the dimension large compared to the sample size in order to have this quantity small. Okay, so if we look at the sort of estimates that we get in this setting and think about what happens in terms of sensitivity to perturbations of the inputs x, it's easy to see you're going to, because we're taking the noise in those inputs and injecting it into the theta hat, right? Where we have a linear estimator, and so that noise component epsilon, that noise vector, appears in a transformed form in theta hat. So a perturbation in that direction can change the output enormously, right? We have something that has an energy that's proportional to the sample size, and if we modify an input vector x and I've said in a unit norm vector delta, if we modify x in that direction, it's easy to show that this transformation is lower bounded by something that depends on the kind of scale of the eigenvalues of XX transpose, and we saw how they were concentrated the other day. And then you can get a lower bound on that in terms of the excess risk that we see, right? So if you're in one of these situations, so if the excess risk is bounded by alpha, I mean, and these are very loose inequalities, but still we get a lower bound that's kind of terrible, right? If the excess risk is upper bounded by alpha, then then you get a lower bound that scales like 1 over square root of alpha, right? So if you're doing well in terms of prediction accuracy in this overfitting regime, then you're necessarily very sensitive to perturbations of the input, just in this linear setting. Okay, and similarly, this random initialization story that I told, this business about random linear functions, if we're in an overparameterized setting, then we have a large subspace where precisely this story is happening, right? A large subspace in the linear case that's being ignored when we estimate parameters. So for instance, doing a gradient flow, if we start at some random initialization theta naught and do a gradient flow to minimize the empirical risk, squared error on the data, then we're going to converge to something that is that minimum norm solution plus the projection of this initialization on the subspace orthogonal to the span of the rows of X, orthogonal to the data. Right, so we don't change the initialization at all in that subspace, but in order to have the benign overfitting phenomenon, the subspace that's orthogonal to the data has to be huge, right? We need to have a really high-dimensional orthogonal subspace. And so, we'd have exactly this story in the orthogonal subspace. I mean, depending on the scales of the two things, we might or might not be affected by that. So, for instance, if you had an initialization that was really very small compared to the scale of the theta hat in that low-dimensional subspace, right? Then you may not see such a massive effect from the random initialization. All right. Okay. So that's really all I wanted to say. That there is this phenomenon of adversarial examples. I think is is a really important one in practice. What we're able to show is the case of random parameters for networks involving these ReLU nonlinearities. The result requires bounded depth, but at least as we've set things up, some constraint on depth is necessary, or we're not going to see these adversarial examples appearing. And I think the interesting interesting outcome here is that this phenomenon is arising because these networks are computing functions that are close to linear, and I think that's really interesting direction. Is that something that carries over to trained networks, right, of this kind? Do we see a similar phenomenon there? All right, thanks very much. Yeah. So, right. So instead of making things linear, we have linear affine functions. Yeah. So yes and no. You need to be careful about the scale of the of this extra parameter, right? Because it determines the probability that you'll be way away from the action, or actually having something interesting going on at each node. So, I don't imagine, with an appropriate choice of scale, that it would be difficult to get analogous results. But we haven't gone through those steps. But yeah, I think I don't think it's going to be essentially different. But you do have to keep control of the scale. Similarly, if you think about functions other than the ReLU that have squashing functions, for instance. You have to have the same sort of considerations. What's the scale if you're on too large a scale or too small a scale? Then you're getting things that are quite different. So again, you need to keep more careful control of the scale. The kind of attractive feature of the ReLU here is the scale just goes away. Right? We don't have to worry about it, and we can talk about ratios of change of value versus the original value. Yeah.
One can trick it.
Yeah.
In a malicious way.
Yeah.
And then what? And then what would be the solution? Process there.
Yeah. So. Right. So the increasing depth is suggestive of what you might do. In fact, there's some indication also on the theory side that increasing over-parameterization, not only through increasing depth, but also increasing width, it might be that at least you might be able to represent the same function without this sort of sensitivity. So the practitioners have put a lot of effort into trying to develop more robust methods. So instead of just optimizing performance on a sample, they're looking for a kind of minimax re-express things as a minimax optimization problem. You know, maximizing the loss over some neighborhood of an input point. So, you know, this is an approach that people take in practice. I don't think there's anything too compelling in theory about you know, how well those methods should work. But yeah, there is some indication that you know, you can get better solutions in a more overparameterized setting, which I think is an interesting direction.
So you briefly mentioned the paper where they are creating adversarial examples for small incoming rules, right?
Yeah.
Do you think you can achieve such behavior with your method if substantial gradient?
Achieve such a behavior? I'm not sure I understand.
So you create some perturbation just adding the gradient multiplied by the constant.
Oh, I see. And then show.
For example, the coordinate of this sample of the gradient, and it will differ from the original example coordinates. You'll be able to create
It sounds plausible, but I don't know. Yeah. I guess I was kind of dismissive of, you know, measuring deviations in Hamming loss, just because actually in the argument that they give, you really do need a large change of the small number of coordinates, which doesn't seem like it's the same phenomenon at all. But yeah, it may be possible to demonstrate a similar thing, a sort of sparsification of the perturbation. Yeah.
Question. So it
Yeah.
looks like a linearity of the network is a weak point for the network. So is it possible to choose the sigma in a way such that linearity doesn't hold?
Yeah, I don't know if it's a weak point. I mean, I think linearity plus this sort of random choice of a linear function, you know, that's where this phenomenon comes from. Is it possible by changing the nonlinearity to change this property? Yeah, I don't know. I mean, I think if you're in a setting, so if you're thinking about the random initialization as that we studied, I mean, I think this neolinear property for, in some sense, sensible initializations is likely to be, you know, quite a universal thing. Yeah. So I'd be surprised if you weren't able to show a similar thing for a range of nonlinearities. But as I say, you would need to be more careful about the scale of initializations in those cases, in many of those cases. Yeah. Anyone?
No question. At least second angle that general formula works for general nonlinearity. It's a different formula, of course, depending on activation, but they're trying to complicate such angles together over that in general should work for nonlinear.
In some sense, that's showing that it's going to be far from linear when you iterate those things a lot. So yes, I guess if you compute those sorts of the evolution there for different nonlinearities, you know, certainly some will converge faster than others. Yeah. So the dependence on depth is going to be different. Yeah, that's a good point. Thank you.